guys, so now that we've talked a ton about all these different kinds of things we can do with exponential and logarithmic functions, we are going to use them for modeling. So just like with polynomial modeling and how that was using polynomials to model real-life situations, we are going to use exponentials to model real-life situations. The cool thing about exponential modeling is that it's actually far more applicable to the real world than polynomial modeling. Polynomial functions are much less likely to occur in real life, but exponential functions are highly likely to occur in the real world because a lot of biological processes are feedback driven. So, for instance, the more rabbits you have, the more rabbit babies you're going to have, which then means that you have more rabbits on top of the rabbits you had before, and then those more rabbits are going to have even more rabbit babies, and that population is going to grow exponentially. There's a lot of ways that we see this in the real world. With the spread of disease, the more people that have a virus like coronavirus, the more people are going to contract the virus. Then since the number of people who have the virus is larger, they're likely to infect more people. So a lot of things in the real world are modeled exponentially. So let's talk a little bit about how this works exactly. So let's start by talking about exponential growth. So suppose a single bacterium divides every hour. So that means that at t equals 0, we have one little bacterium. Our count is 1. So this bacterium divides every hour. So at t equals 1 hour, after 1 hour has gone by, we now have 2, right? Because he divides into 2 more bacteria. So we have 2. After another hour, how many are we going to have? Are we just going to add 1 more? No, we're going to have 4, because each of these 2 bacteria are splitting into 2. So now we have 4. At t equals 3, each of these 4 bacteria are going to divide, so we have 8. At t equals 4, you can probably see what's going on here. Each of these bacteria divide, and we have 16. And this continues. It would get a little bit ridiculous drawing 32 of those guys. So let's look at these numbers. So what exactly is happening to them? So we start off with 1, clearly. Then we double this 1 that we had. So 1 times 2, right? Before we had 1, and we're multiplying by 2. Now this time, we're multiplying this 2 by 2. So we have 1 times 2 times 2, right? This was our amount from before, and now we're doubling it. With 8, now we're taking this 4 and doubling. So we add 1 times 2 times 2 from before times 2. And then for 16, again, we had all of this, 1 times 2 times 2 times 2, doubled. Can we condense these at all? Well, again, this is obviously 1. How many times does 2 show up here? once. So maybe let's write this as 2 shown up once. Over here we've got 2 how many times? It's shown up twice. How can we write 2 times 2? Maybe 2 squared. And this pattern continues. What do we have here? We've got 1 times 2 cubed. That's how many times 2 shows up here. And 1 times 2 to the 4th. So all of this continues. We could sort of say here that we have 1 times 2 0 times, so 1 times 2 to the 0 power. So how can we write this more generally in terms of the time that's gone by? Well, what do we notice when we compare what's written here to the time? At t equals 0, we have 1 times 2 to the 0. At t equals 1, we have 1 times 2 to the 1. At t equals 2, we have 1 times 2 to the 2. Every hour, our time matches the exponent on this 2 here. So this can be modeled by f of t equals 1 times 2 to the t, right? We get this because all of these exponents match the times that they model. So at some time t, we have 1 times 2 to the t. So the amount that we've started with times the number of times that it's doubled. Suppose we start with 10 bacteria. I'm not going to draw all of these because that would get pretty ridiculous, but at t equals 0, how many are we starting with? Well, it says we're starting with 10. Then at t equals 1, we know that this bacteria is going to double or divide every hour. So every single one of these bacteria is going to split into 2. So we have 10 times 2, or 20 bacteria. Let me just go ahead and write these in. At t equals 2, how many bacteria are we going to have? Well, we know this is going to double again, so we end up with 40. Then at t equals 3, we have 80, and t equals 4, we have 160. So let's look at how we can express this sort of in the same way as we did before. So here we're starting with 10, and how many times have we doubled right when we're starting? We haven't doubled yet, right? No time has gone by. An hour has not passed yet, so we have 2 to the 0. At t equals 1, we've had 1 hour go by, so we have 1 division, or 1 doubling. At t equals 2, it's doubled twice. At t equals 3, it's doubled 3 times. And at t equals 4, it's doubled 4 times. So looking at this, how do you think we can model this equation? This is modeled by the number that we started with times the number of times that we've doubled, right? So at time t, we've doubled t times, right? The number of hours that have passed is the number of times that we have doubled. So we're starting with 10, and it doubles t times. Suppose the bacteria divide every 3 hours. Okay, so this one is a little bit more tricky. At t equals 0, again, we're starting with 10. At t equals 1, do we know anything? We actually can't really know exactly how many bacteria we have, right? Some of them might still be in the process of dividing. We may be partway through a cell division for these bacteria. So we actually don't know what's happening after 1 hour because we don't know that it's divided completely until 3 hours. So what about t equals 2? Same thing there actually, right? We're not sure. At t equals 3, we know that we have doubled at this point. So we have at this point 10 times 2 to the 1. At t equals 4, we don't know. We have to wait until we get again to t equals 6. At t equals 6, we've doubled twice, right? Because 2 periods of 3 hours have gone by. At t equals 9, 3 periods of 3 hours have gone by. So we've had 3 divisions. So how are we going to be able to model this? We need to make it so that our exponent on the 2 is 1 when t is 3. We need to make it so the exponent is 2 when t is 6. We need to make it so that the exponent is 3 when t is 9. How can we 1 from 3, 2 from 6, 3 from 9? How can we make 3 become 1, 6 become 2, and 9 become 3? We divide. Divide by 3. So our model here again, we're starting with that 10 that we started with, and then we're doubling every 3 hours. So our exponent is going to be our time divided by 3, right? So if we have t equals 3, then we have an exponent of 3 over 3, which is 1. If we have t equals 6, we have an exponent of 6 over 3, which is 2. If we have t equals 9, we have an exponent of 9 over 3, which is 3. So that's exactly what we want. So what does this mean in general for exponential growth? In general, we can model doubling growth by the following. F of t equals n times 2 to the t over d. So what do each of these things mean? Well, f of t is the amount at time t. Maybe it's fish, maybe it's bacteria, maybe it's money. Could be any of these things. It's our amount of whatever we're talking about. N is the initial amount. T is time, and, right, T is time. And D is what we're going to call the doubling time. The doubling time just meaning the amount that it takes for whatever we're talking about to double. One note here is that our units must be consistent. So if we're talking about something that doubles every 2 hours, then our time, whenever we use it, needs to be 2 hours. If we're talking about something that doubles every 3 years, then our time needs to be in years. So let's look at a couple of examples of this in the lab manual. I'm going to start off with number 1. So a certain culture of bacterium starts with 10 bacteria and doubles every 1.3 hours. So very similar to the problems we were just talking about. We want to determine a model, N of T, for the number of bacteria in the culture after T hours. I'm just going to change this to ask for F of T. All right, so number of bacteria after T hours. We know that we have our formula that we just talked about. So F of T equals N times 2 to the T over D. And all we really have to do here is fill out all the necessary information. So it says we're starting with 10 bacteria. So that's our N value, our initial value. And it's doubling every 1.3 hours, so that's our doubling time. Simple as that. So our formula here is 10 times 2 to the T over 1.3. Oh, it's that easy. Estimate the number of bacteria present after 35 hours. So again, our formula tells us that F of T is our amount at time T. So what is this asking us for? Very important for us to be able to take these verbal statements, right? These statements that are in words, and think about it, what it means mathematically. So number of bacteria present after 35 hours would be the amount of bacteria at time 35. Awesome. So F of 35 just means that we plug in 35 for T here, right? We want to make them match. So 10 times 2 to the 35 over 1.3. And with that, we can just throw it into our calculator. So 10 times 2 to the 35 divided by 1.3. We want to make sure we use parentheses in that exponent. And we get a ridiculously large number. 1,272. So many bacteria. Kind of gross, actually. And that's really sort of the interesting thing about exponential functions is how big they get so quickly. So 35 isn't actually that long of a time, right? But this is a huge number. So exponential growth functions grow very large very quickly. All right, so here's an interesting question. When will the bacteria count reach 10,000? When is this going to occur? So what is the time? When our bacteria count is 10,000. So what do we want to be equal to 10,000? It's our bacteria count. What's the name that we've given to our bacteria count? F of T. So T equals what when F of T equals 10,000? All right, well, let's replace F of T in our formula with 10,000. So 10,000 equals 10 times 2 to the T over 1.3. and solve. So the nice thing about this is that this is solving exponential functions from our last lesson. We've got to isolate our exponential first. So that means we've got to get rid of any coefficients that we have. So let's get this 10 over to the other side. So we've got 10,000 divided by 10, which leaves us with just 1,000. Now we've got the exponential totally isolated, so we can rewrite it in logarithmic form. We've got to do base to base, so we've got log base 2 of our old output was 1,000, so that's our new input, and our exponent gets exiled, so we've got t over 1.3. And now the last thing to do is just solve for t. So to solve for t, we just have to multiply by 1.3. So t equals 1.3 times log base 2 of 1,000. So let's go ahead and put that in our calculator. If you have one of those nice TI-36X Pro calculators or whatever, you can just hit your log button multiple times and it will give you a log with a base. I can't do that on my calculator. It takes a little bit of extra work to do so. So instead of doing that, I'm going to use this formula. Log base b of a is equal to log of a divided by log of b. So to calculate 1.3 times log base 2 of 1,000, I'm going to do 1.3 times log of 1,000 divided by log base 2. So I'm getting 12.956. And what does this represent here? Again, it's really important for us to always be thinking about what everything is representing. So 12.956, what is that? Well, what were we looking for? We were looking for the time that f of t was equal to 10,000. So this is our t value, so it's hours. And what this means is that it's going to take 12.956 hours approximately for the number of bacteria to reach 10,000. Okay, a certain species of rabbit was introduced to France 40 years ago. The population doubles every 8 years, and now there are 9,600 of them. So what was the initial size of the rabbit population? Let's write a formula for this. So f of t equals n times 2 to the t over d. That's our kind of skeleton formula, so let's fill it in. So what do we know here? We know that the rabbit population doubles every 8 years. So what is that? 8 years, what can we plug that in for? Do we plug it in for t? Not quite. We want to plug it in for d, right? 8 years is our doubling time. So far we know that f of t equals n times 2 to the t over 8. All right, how are we going to find our initial value? We've done stuff like this a lot. Hopefully we're sort of getting to the point where we remember what we need to do in cases like this. So when we're trying to solve for a variable, we just plug in a point for these two values. So what points do we have? What do we know here? Well, we know that now the population is 9,600. So we know that the amount of rabbits is 9,600 when? What is the t value that gives us 9,600? Well, now. How long? When is now? How long has it been since the rabbits were introduced? It's been 40 years. So we have 96 rabbits 40 years after the rabbits were, after our initial. So t equals 40 in this case. That means that we have f of 40 equals 9600. So let's plug that in. So we know that f of 40 is 9600, first of all, but it also is n times 2 to the 40 divided by 8. Well, it's just 5. And 2 to the 5th is 32. So we know that 9600, right, taking that guy from here and this guy from here, we know that 9600 is n times 32, so n is 300. So what is 300? Well, our n value, which represents what? The initial size of the rabbit population. So our initial size was 300 rabbits. And that's the answer to the question. Estimate the size of the rabbit population 5 years from now. Okay, well, let's write down our formula now that we have all the pieces. So we have n, which is 300, times 2 to the t over d, which is 8. T over 8. All right, so what are we going to do? Are we just going to plug in 5 to this equation? Not quite. We want to remember that it's asking 5 years from now. But when did we say that now was? We said now was t equals 40. So 5 years later, what's our t going to be? It's actually going to be 45. So we need to plug in 45 rather than 5 for t here. This is going to be less of a nice number, so let's do this in our calculator. So we have 300 times 2 raised to the 45 divided by 8, and we get 14,805 rabbits in the population. Great, okay. Y'all try this next problem on your own, and we will talk about it in office hours. Now I would like for us to talk about half-life. So let me define that really quickly. Half-life of a substance is the amount of time it takes for some amount of the substance to decrease by 50%. So the amount of time it takes for something to be halved. Let's look at an example of half-life. The half-life of caffeine is 5.7 hours. what does this mean exactly? So let's suppose that at noon you take a drink of coffee. So you drink 200 milligrams of caffeine. What this means is that 5.7 hours later, at around 5:45, you still have 100 milligrams of caffeine in your system. That also means that 5.7 hours after that, around 11:30 at night, you still have 50 milligrams, right? In one interval of 5.7 hours, the original amount has halved. And then that doesn't mean that it's going to take 5.7 hours for the next 100 to disappear as well. The amount at the time that we're starting, that 5.7 hours, is going to be halved. So we have 50 milligrams left. It actually might take a lot longer for something to leave your system than you think. So how would this potentially be modeled? So this is modeled by f of t equals, so how much did we start with? We started with 200. And instead of doubling like last time, every period of time we are dividing by 2. So we are dividing by 2 every 5.7 hours. In general, we can model half-life by f of t equals the initial amount times 1/2 to the t divided by h. So again, f of t is the amount at time t. N is the initial amount. And h, this time, is the half-life. And again, we have our condition that the units must be consistent. Okay, so let's give this one a shot. So this one might seem familiar to those of you who have taken chemistry. The half-life of cesium-137 is 30.2 years. Suppose we're starting with a sample that has a mass of 1 kilogram. So we want to write the function first. So m of t, that models the mass remaining after t years. So our formula looks like this. Make sure my h looks different from my n. What does this n represent? Represents the amount that we're starting with. We're starting with 1 kilogram. So n is 1 here. Times 1/2 to the t. right? T is our independent variable in this situation. So it stays as T. We don't want to plug anything in for that yet. And our half-life is what? 30.2 years. So this is my equation. All right, the second question is asking how much of this stuff will remain after 151 years. So what is the amount? So what is m of t? Is what? After 151 years have gone by. So t equals 151. How can we write this otherwise? What is m of 151? So let's find it. So if t is 151 over here, then t has to be 151 over here. (151) divided by 30.2 just so happens to be 5, which gives us 0.03125. So again, what does this represent? So we have 0.03125. What were we looking for? Well, we were looking for the amount at time 151. So since this is our amount, this is going to be the kilograms of cesium left after 151 years. Okay, the next question I want to work through is this guy. So, example. All right, so let's use our formula. So we know we've got f of t equals our initial amount times 1/2 t over h. So let's fill it out. So what do we know? We know our half-life is 5,730 years. Do we know our initial? We don't know our initial. So what are we going to be able to do? So what are we looking for? We're looking for how old. So how many years have gone by since we had our initial amount? So t equals what, right? We're talking about when, how old. When what is the case? So we want to know when we have 22% of what we had originally. Is 22% of original. What is the original amount? Well, we don't know, but we know for now that it's n. What's another way of writing this mathematically? So the amount we know is represented by f of t. So when is the amount? 22% of the original. So how can we write 22% of the original? 22%, we know we write that as 0.22 times n. Let's use that and see if it does anything for us. So we want to replace f of t with 0.22n. So we've got two variables here. We only want to have one variable, right? That's the way we solve for something. So let's continue with this function and see what happens. So what would we need to do here to solve this? The first thing we would need to do is to isolate the exponential, right? So in order to do that, let's divide by the coefficient here, which is n. So if I divide by n on both sides, I've canceled out this n, and I'm also canceling out this n, right? So I'm left with 0.22 equals 1/2 t over 5,730. Now look at this. First of all, we've got an exponential that's been isolated, super great, and we've also easily gotten rid of n. So the point here actually is that when you're looking for a percentage of how much of a substance is left, it doesn't matter what the initial amount was, right? We can solve this without knowing the initial amount if we want to know how long it's going to take for there to be a new percentage of the substance. We don't need to know how much we started with, because this exponential is going to give us that percentage. How do we continue from here? Well, we've got an isolated exponential, so let's switch to log form. So base to base, we have log 1/2, I'm going to write 0.5, of our original output, so 0.22, equals t over 5,730. And then to solve for t, we just multiply by this denominator. So 5,730 times log base 0.5 of 0.22. Let's throw that into a calculator really quickly. I'm getting 12,516 years. That's super old, but I guess that's how old fossils are. Now that we've talked about doubling time and half time, I want to sort of expand our discussion, because we are not always aware of how long it takes for something to exactly double or exactly half. So in other situations, we may be given the percentage of something left after a certain time period. So let's look at that really quickly. For an initial amount n increasing by rate r per time period, the amount present after t time periods is f of t equals n times 1 plus r to the t. I'll talk more about this in just a second. If n is decreasing, by rate r, f of t equals n times 1 minus r to the t. So how does this fit in with what we were doing before? Well, we still have that initial stuff. Remember, when we were doubling, the way that would fit in here is that we have our initial amount, which was 1, right, plus every time we grow in a doubling situation, we're doubling, right? So we're adding 1 more of what we had before, right? Growing by 100%. We have an extra 100% of what we had originally. So here r would be 1. So that our inside, our base of our exponent is 2. And then our exponent represents the number of times that we've grown by that much, right? So we always were dividing the amount of time that's passed by the doubling time. So that means that in that situation, the number of times that we've doubled is what's in our exponent. Here, that's what we're saying, the amount present after t time periods. So t, our exponent, is representing the number of time periods that have gone by since we've grown this much. Okay, so let's look at an example of this. Okay, let's use our formula. So f of t equals n times 1, plus or minus. We are growing, we're increasing, so we want to add. So it's growing. Here, our initial is what? 10, right? 10 bacteria. Our rate is 15%, so that means that R is going to be 0.15. And T, what are we going to use here? So remember, this 15% is the amount that's growing per hour. Are we going to say 1, because 1 day has gone by? We're not, right? If our rate is growing by 15% per hour, we need to use hours for our units, right? Remember, our units need to be consistent. So 1 day is 24 hours. So our T needs to be 24. So let's plug that all in together. F of t equals 10 times 1 plus 0.1 plus 0.15 to the 24th. So again, we're plugging in 24 for t. I messed that up, sorry y'all. We can plug this into our calculator. We got 10 times 1 plus 0.15 raised to the 24th, and we get 286.2. Oh, we don't need to use decimals here, right? Because we're talking about number of bacteria, right? So we've got 286 bacteria. Okay. Okay, so this one is a little bit more complicated. So let's go ahead and write our formula again. We're decaying, which is why we have the subtraction formula. What is our n in this situation? We don't know. Is that going to be a problem for us? Think back to about 2 problems ago. Remember, we didn't know how much of the fossil we had, but we ended up not needing it, right? Because we were looking for a percentage. In this case, are we looking for a percentage as well? Let's think about it. So we're looking for a time, right? Half-life is the amount of time it takes for something to decay by 50%. So time, when what is true? When our amount is half of what we started with, right? So 1/2 or 0.5 of our initial. It's okay that we don't know what our initial is right now. What is R? Well, we know that we're decaying by 20%. So 20% means 0.2, right? We want to move the decimal over 2 spaces to the left. So let's go ahead and plug all this in. So we have 0.5n equals n times 1 minus 0.2 to the t. So let's do a little bit of simplification so that it's a little bit clearer what we should do next. So we have 0.5n equals n times 0.8 to the t. Okay guys, I'd like to make the note that here when we have this n times 0.8 to the t, what's happening is that at every time period, similarly to how we would double every time period or half every time period with those respective formulas, this time we have 0.8 of what we had before, right? If 100% is what we had initially, then after every time period, when 20% decays, we're left with 80% of what we had originally. All right, we've got these two variables. We want to get rid of one of them so that we can solve for t, right? We want to get rid of n so that we can solve for t. We want to get the exponential on its own, right? So let's do that. We can do that by dividing by the coefficient. So we divide by n. These guys cancel, and so do these guys. So since we've divided by n, we're left with 0.5 equals 0.8 to the t. Once we've isolated the exponential, we just write it in log form, right? So we have log base 0.8 of 0.5 equals t. From here, we can just plug that into the calculator. We get 3.106 years. So the half-life of this element that decays at 20% per year is 3.106 years. Now let's talk a little bit about compound interest. This is another type of exponential growth. And it specifically has to do with money. So, definition, interest is money paid to someone regularly for lending you money. The amount paid is a percentage called the interest rate of the money lent. Calculating this amount is called compounding. Okay, so this one is going to be a bit more complicated than our other formulas. So f of t, or the amount at time t, here, we have p, which is actually our initial amount. WebAssign calls this the principal amount. this is the amount that someone borrows initially. So 1 plus R this time over N. Here, R is the annual interest rate. And we want to make sure that it's a decimal. N is the number of times compounded per year. And T is the time in years. Okay, so let's use this formula a couple of times. There are a couple of good examples in the lab manual. Eagle Bank offers a savings account that earns 2.9% compounded quarterly. So 2.9% quarterly is important, and you have $1,000 to invest. You may see words like quarterly, monthly, yearly, semi-annually. So each of these things, how many times are they going to happen per year? So if it's compounded yearly, it's just once, right? How many times does it happen per year if it's monthly? 12. What about quarterly? How many quarters are there in anything, much less a year? 4, right? If it's semi-annually, it happens twice. Write a function that models the money in the account after T years. So let's pull out our formula. P1 plus R over N to the N times T. So the things we need to know here are P, R, and N. So P is our principal amount. It's the amount that we're starting with. What is that here? Well, it's $1,000. And then it's earning 2.9%. So what is that in decimal form? We've got to move the decimal over twice. We've got 0.029. And then N, again, number of times we compound in a year. So if it's being compounded quarterly, it's happening every quarter, so that's 4 times. So our formula is going to give us 1,000 times 1 plus 0.029 divided by 4 to the 4 times T. How much money will you have after 10 years? Okay, so after 10 years, that would be the amount that we have at time T equals 10, right? So F of 10. So let's plug that into our formula, simple as that. So we've got 1,000 times 1 plus 0.029 over 4 to the 4, and instead of T, right, we're plugging in 10 for T. So we've got that up there. Let's simplify a little bit so it's a little bit easier to put this stuff into our calculator. So 1.00725, and then 4 times 10 is 40. So we put this all into a calculator. And we get $1,335. What number did we just find? how much money we have after 10 years, right? So what are the units on this? Dollars. And let's go ahead and round it to 2 decimal places. How many years will it take you to have 1,700 in the account? All right, so how many years means we're looking for a time. So t equals what when the amount in the account is 1,700. So our amount at time t is 1,700. So looks like we've got to replace f of t with 1,700 and solve for t. So let's use our formula. So 1,700 equals, I'm going to go ahead and use this simplified base here, but remember we've got this 1,000 times 1.00725 times to the 4t. We want to solve for t here, so we've got to get this out of the exponent. Before we can switch, so we've got to solve this exponential equation. So let's get this exponential isolated. So let's divide by 1,000. So we end up with 1.7 over here. 1,700 divided by 1,000 is 1.7. is equal to 1.00725 to the 4t. So now the exponential is isolated. Let's go ahead and switch to log form. So we have log base 1.00725 of 1.7 equals 4t. So t here is all this log base 1.00725 of 1.7 divided by 4. And that number is oops, actually I wrote the wrong thing initially. The answer is 18.36 years. Number 3 here. So Double T Finance is offering an account that earns 3.25% compounded monthly. How long will it take the money in the account to double? So let's pull out our formula. F of t equals p times 1 plus r over n to the n times t. Okay, so what are we looking for? We're looking for how long. So t equals what when what is true? Well, we want the amount of money in the account to double. So we want to have twice what we had initially. How can we say that mathematically? Well, we know we're talking about the amount in the account. So f of t is double what it was originally. How much is it originally? Well, we don't know, right? Nothing in this says anything about how much we're starting with. But we know that we're representing it with p. So when is our amount going to be twice what we started with, or twice p? 2 times p. So let's plug this in for f of t here. What is r for this problem? What is our annual rate? Well, it's that 3.25, right? So 0.0325. We can't forget to move that decimal over. And it's compounded monthly. So how many times per year is it going to be compounded? 12, right? 12 months in a year, so we're going to compound it 12 times. And we're solving for t. At this point, we've seen that our first step when we have something like this is just to divide out the initial amount. So these p's are going to cancel. So we're left with 2 equals 1 plus 0.0325 divided by 12 to the 12 times t. I looked at this in the calculator, and it's an irrational number, right? It doesn't stop very early. And so because of that, in order to not lose any information, I'm going to leave it like this. So let's switch it to log form. When we put this in log form, we have log base to base. So our base here is all this, 1 plus 0.0325 divided by 12. All that of 2 is equal to 12 times t. So t equals log base 1 plus 0.0325 divided by 12 of 2 all over 12. If I plug this into my calculator, I get, log base 1 plus 0.0325 divided by 12 of 2 all divided by 12. The answer that I get is 21.356. What is the unit on this? Is it money or time? Are we talking about money or time? We're talking about time, right? We're looking for t. This is t. So this is in years. A lot of banks these days have moved to continuously compounded interest. Continuously means that it's happening at every moment. So, definition: continuously compounded interest is compounded at every instant. So instead of compounding once every month, or once every quarter, or once every year, or once every 6 months, we are compounding at every moment of every day. This is modeled by f of t equals p times e to the rt. So again, this is amount at time t. P is still our principal amount, which is just the initial amount. E is E, right? E is just a number. And R is our rate as a decimal. And again, I want to point out that T is always in years for interest problems. So before we could use days or months or whatever for T or hours, but for interest problems, we always want to use years. And that's just because our rates are always annual. Okay, so let's go back to that same page in the lab manual. So Euler Money offers a certificate of deposit, which is just another way that a bank can borrow money from you. And it's earning 5.1% compounded continuously. I know this doesn't look like it would be pronounced Euler, but that's a famous mathematician, and that's how you pronounce his name. So this first question is asking us to write a function a of t that models what this is worth after t years. So let's use our formula. Let's start with our formula. So p times e to the rt. What is p here? Well, this person has $10,000 to invest. So a of t, we replace p with 10,000. E is just a number. What is r? Well, it's earning 5.1% compounded continuously, right? So 0.051 times t. Calculate how much money this will be worth after 3 years. So the amount in 3 years, or at time t equals 3, just means we have to plug in 3 for t. So 10,000 times e to the 0.051 times 3. We plug this into our calculator. E to the 0.051 times 3. And we get $11,653.24 Okay, how many years will it take the CD to be worth $20,000? So how many years? So that's asking, what is our t? When it's worth an amount of $20,000, so when our amount is 20,000. All right, let's use our formula, but replace a of t with 20,000. Okay, first step that we want to do is isolate the exponential, so divide by this coefficient. We end up with 2 on this side is equal to e to the 0.051 times t. And let's look at this for a second. So we know that 20,000 would be double what we started with, right? Double the 10,000. But it doesn't even matter that we started with 10,000, right? If this question had just asked us, how long will it take for the account to double? We would know that regardless of whether we started with $10,000 or $5 or $1 million, right? It's gonna take the same amount of time to double. So now we can switch to log form. Our base is going to be ln, right? That's the inverse of e to the x, or log base e, right? You could totally use that as well, of 2 equals 0.051 times t. So t here is ln of 2 divided by 0.051. And that's super easy to put into our calculator. And it gives us 13.59 years. All right, last question on this page here says Koshi Savings, that's another weird math person name, offers a savings account that earns 2.2% compounded continuously. How long will it take the money in this account to triple? So let's pull out our formula. We are compounded continuously, so we're going to use this guy. We don't know what P is. We're not sure what our principal is. But we know that our rate is 2.2%. What are we looking for? Well, how long? That's an indicator that we're going to be looking for a T value. Will it take the money in this account to triple? So what T value do we have when money in the account, so the amount at time T, is triple what we started with? So how can we express that mathematically? Well, the amount we started with is P, so triple the amount we started with would be 3P. Let's replace f of t with 3P and solve for t. P times e to the r we said was this 2.2%, so we put that in decimal form. So 0.022 times t. Okay, so we want to isolate this exponential, so we can divide by p over here. But when we divide by p on both sides, this p goes away, right? That's why we're dividing, is to get rid of this guy. But when we divide over here as well, these guys cancel. We're left with 3 equals e to the 0.022t. Let's switch that off into natural log form. So ln of our old output was 3. That's our new input. And it's equal to our exponent, so 0.022 times t. That means that t is ln of 3 divided by 0.022. Let's throw that in our calculator. So this is 49.94 years. Another cool thing about this is that we can actually use continuous growth to talk about all kinds of exponential growth and decay. So, for example, continuous models so using E are used often because E has a lot of important properties. So it's actually not just used in the context of compounding interest. And we can actually use it for the types of problems that we've already seen. So for example, let's say that we have a small town and it has a population of 7,360. So I guess not the smallest town, but pretty small. And it doubles every 30 years. This is a doubling time problem. We can totally represent this using doubling time. So let's look at that really quick. What would that look like? With our doubling formula, we would have the following situation, right? So our doubling time formula looks like this. what can we fill in here? Well, we know that our initial, we're starting with 7,360 times 2 to the t. We don't know how much time has gone by, but we know it doubles every 30 years. That's our doubling time. Our continuous formula, so that guy is this one, e to the RT. I'm going to use n here instead of p, just so that it sort of matches up more with this one. We know that n, again, is 7,360, but we don't know what r is. However, we know that in 30 years, this is going to be double what we started with. So when t equals 30, so in 30 years, f of t is going to be equal to 2 times what we started with. So let's replace f of t here with 2 times 7,360. So 2 times 7,360 is equal to n, which is 7,360, times e to the r times 30, right? Remember, t is 30. And let's solve for r. So we want to divide by this coefficient. So we divide by 7. These cancel, these cancel. We get 2 equals e to the r times 30. We switch to log form. Base to base, we have ln. Our output becomes our input, so 2. ln of 2 is equal to r times 30. So r equals, so that's this guy. So r is equal to ln of 2 divided by 30, which is 0.0231. What does this mean? Well, this means that the continuous growth rate is 2.31%. Okay. A 6.5 kilogram sample of radon has a half-life of 3.8 days. Let's model this situation both ways. So, using our half-life formula, again, this one looks just like the doubling time formula, but we use 1/2 instead, right? So we're initially starting with how much? Our initial amount is 6.5 times, again, we have that 1/2 to the t divided by half-life. Our half-life here is 3.8. Cool. Okay, so let's look at this continuous model. Again, we are starting with this sort of skeleton We know n, again, is 6.5. And we also know when t equals 3.8, what do we know? How much of it is left? What is our amount? It's half of what we started with, right? That's our half-life. That's the definition of half-life. So we have 1/2 of what we started with, which was 6.5. Let's plug all this in. So we know that f of t is 1/2 6.5, so 1/2 times 6.5 equals our initial, so 6.5 times e to the r times t. We know that t is 3.8. That's what we're using here to find r. We divide, these guys cancel. So we have, I'm going to change this to be 0.5 equals e to the r times 3.8. We write this in log form. Base to base, we have ln of our old output was 0.5, so that's our new input. Equals r times 3.8. To get r by itself, we need to divide by this coefficient. So we divide by 3.8, we get ln of 0.5 divided by 3.8. If we throw that into our calculator, we get negative 0.182. So what does this mean about our continuous growth rate? It means that we move that decimal place over, we get 18.2% continuous, decay rate. So I want us to notice something here. I want us to notice that in our first case, the continuous rate, which we've represented with r, is positive in this first situation, right? It was positive. We got 0.0231. So it's positive when we are, what situation was this? We were in a growth situation. So it's positive for growth. And when we compare that to our r for this second problem, r here was negative. Are we in a growth situation for this second question? No, we're talking about half-life, right? We're talking about decay. So it is negative for decay. One last situation where we're going to see continuous growth is Newton's law of cooling. I'm just going to write out the whole thing really quick and then talk about what everything means. So Newton's law of cooling. We have big T of little t, and that's going to represent temperature at time t. A here is our initial temperature. In this case, R is going to represent what we call room temperature. And I put room in parentheses because what it actually is the surrounding temperature. So for instance, in the case where we're talking about something that's going into a refrigerator, this R value is going to be the temperature inside of the refrigerator. It's going to be the temperature that is surrounding whatever object is heating up or cooling down. If we're talking about an oven, right? The oven is going to have a very high temperature, right? The room temperature, or that surrounding temperature, is very high. So it's not necessarily room temperature, which is like 70-ish degrees. It means more like the surrounding temperature. So I'm going to write that surrounding temperature. And then K is a constant that depends on the object. This may be given to you, or you may have to find it. Again, with this guy, we want to make sure we're using all the same units. So if a temperature is given Fahrenheit, we want to continue to use Fahrenheit throughout. If we are talking about temperature after a certain number of minutes, then T needs to be in minutes. So let's look at an example of this. Okay, so we've got a lot of information here. Let's start putting it into our formula to sort of help us sort it out. So what is our initial temperature in this situation? We've just taken it out of the fridge, right? So our initial temperature is this 38 degrees Fahrenheit minus our room temperature. So remember, this is just the surrounding temperature for the object. So we're putting it in the oven. So our surrounding temperature is going to be how hot the oven is, right? So 350 times e to the negative k. Negative k is a constant, again, that depends on the object. It's not given to us here. So we don't know what that is yet. T, we don't know quite yet either. Plus 350. All right, so we need to figure out what k is here. All right, we've seen many problems where we end up with an extra variable that we need to figure out. And how have we done that in the past? Well, we know that the other two variables that are left over are little t and big T of little t, right? So our input and our output. So in order to find k, the easiest way for us to do that would be to plug in some input and output. What do we know that we haven't used yet? This information about the 15 minutes and the chicken being 70 degrees, right? After 15 minutes, we know that it's heated up to 70. When T equals 15, we have that our temperature is 70. So we can replace big T of little t with 70 and little t with 15. So let's go ahead and do that. So we have 70 equals 38 minus 350 times e to the negative k times 15 plus 350. Okay, let's get to solving for k. So this time we've got a little bit more to do than normal. We know we want to combine these guys. So 38 minus 350 gives us negative 312. In order to isolate this exponential function, we've got to get rid of everything that's multiplied to and added to it. So let's subtract by this 350 first. So 70 minus 350 is negative 280. So we're subtracting this guy over. This guy again is equal to negative 312 times e to the negative k times 15. All right, so I divide 280 by 312. It doesn't give me a super nice decimal, so I'm going to leave it as 280 divided by 312. But I am going to get rid of these negatives, right? Because a negative divided by a negative is just a positive. So we've got 280 divided by 312 is equal to e to the negative k times 15. We now have an isolated exponential. So we can go ahead and switch to log form. So we end up getting the inverse of e is ln, right? Log base e. Our output before was 280 over 312, so that's my new input. And then my exponent was negative k times 15. And so that's our new output, right? The exponent gets exiled. So last thing to do to get the k by itself is to divide by negative and the 15, right? Get that to the other side. So we have ln of 280 divided by 312 all over negative 15, which comes out to be 0.00721. Okay, so we found the k value. Let's go ahead and write that formula out. So our whole formula here is this guy equals negative 312 times e to the negative 0.00721 times t plus 350. Okay, are we done? We are not done. Our question, the full question, is asking us how long does it take to cook the chicken? So what is that asking mathematically? Well, it's definitely asking for a t value. How long, right? So t equals what? So how do we know when the chicken is done cooking? Well, we said that it's done when it reaches 180 degrees Fahrenheit. So in order for it to be done, we want our big T of little t to be 180. Looks like we've got to plug in 180 and solve for t. So 180 equals all of this. Before we move forward, I sort of want to look at this equation and look at what it looks like and see what it looks like and talk a little bit about what's going on. So let's go ahead and do that in Desmos. I'd like for us to look at this and see how the graph is moving. I would like for us to notice that we have that y-intercept at 38, right? That's our initial temperature where T equals 0. As T increases, we notice that the graph is getting larger in an exponential way, and we're approaching, but not quite touching, that line that is at 350. So we have this horizontal asymptote at 350, right? Because the longer something stays in an oven that's 350 degrees, the closer to 350 degrees it's going to get. So now that we know a little bit more about what's going on, again, we're plugging in this 180. We're trying to figure out where this all is equal to this. So let's do it algebraically. So in order to get, we want to get this by itself. So we subtract that 350 over, we get negative 170. Then we divide over. Again, those negatives will cancel each other out, so we just have 170 over 312 is equal to E times negative 0.00721 times T. The exponential is isolated, so we can go ahead and write it in log form. Well, we have a base of E, so our log is going to be ln. Our old output was this fraction, so that's going to be our new input. And this is going to be equal to that exponent. So we know T here is ln of 170 over 312, all divided by negative 0.00721. And we get 84 minutes. So this is how long it takes the chicken to reach 180 degrees so that it's done. So our general graph here looks like this. We're starting out at 38 degrees Fahrenheit, and slowly over time we are starting to get really, really close to that 350. So we have this horizontal asymptote here, right, that we're approaching, but not quite ever touching. And this question has asked us, when do we reach 180? So it's asking us to find, we've been asked to find this T value, right? And we did find it. We said that it was 84. Well, it's hotter for the rest of this function, right? So it's hotter than 180 degrees Fahrenheit when our temperature is larger than 180 degrees, which is what part of the graph? It's this portion, right? It's all of this. What time represents that? So when? What time is that? Well, it's all of the minutes after 84. So our interval here would be 84 to infinity. Okay guys, thanks so much for paying attention to all of this. I know this is a long lesson. You guys are doing great. And let me know if you have any questions about the material. Thanks guys. To comfort you, although look what's the best I